synthesis. So just to review where we were at last time, we were thinking about these challenges. And I must say here, when we go through a couple of these problems today, this can either be almost fun or probably like just really frustrating, depending on how you look at it. It's almost fun if you look at the puzzle solving aspects of it. But as I mentioned, I'll make this bigger, it can also be quite frustrating. So the goal was here, we have this compound in the top left, this alkyl bromide. The stereochemistry is not important. This is what we have on our shelf, let's say, and we want to turn this into this compound on the right. So we want to then synthesize this new compound with this bromine here. Now, we don't know a way of doing it in one step, actually from this compound on the left. Actually, if you just had the compound without the bromine there, you could do a radical reaction to introduce the bromine, but we'll pretend we don't have that compound. So we want to move this bromo substituent here from this position that I'm circling over to the left one. And a systematic way of approaching these synthetic problems is to ask these three questions first. Have I changed the number of carbons? And here the answer is no. Have I changed the identity or the type of the functional group? Here the answer again is no. It's a bromo, and then it's a bromo. Have I changed the location of any of the functional groups? And there the answer is yes. And so what we want to do is be able to have this bromine hop over here to the left. And we don't know the way, as I mentioned, to do that in one step, but we can break it down systematically in two steps. And these are using organic 1 reactions where we're going to carry out an elimination reaction. There's sodium hydroxide, water, and heat, and use a little base, sodium hydroxide, not a big bulky base, because we want to generate the more substituted, more stable alkene that we have here. And then next, we're going to add HBr, and hopefully you had seen a reaction that we can add HBr as just this reagent alone to generate what's known as the Markovnikov product. So the bromine is on the more substituted carbon. Or if we added HBr in the presence of peroxide, then we would generate what's known as the anti-Markovnikov product, a radical reaction, another bromine here on the less substituted side. So you can start to piece together these different reactions to basically move functional groups around. And then last for our synopsis from last time here is a way of thinking about it. This seems very cumbersome for this short synthesis, but for a really long synthesis, and I'll try to show a slightly longer example in a few minutes. So it's an idea of retrosynthetic analysis. And this is this tool that was developed to come up with a systematic way of thinking about how to make compounds. And you think backwards. You'd start with the final compound. So in other words, this is what we want in the end, or the product. And you start thinking backwards, and what could you make that from? And you say, okay, if I had this alkyl bromide, I know I could make that from this alkene. And I know I could make this alkene, let's say, from this compound, if that's what I had on the shell. And so this is a way of thinking backwards. But what's really important, and I just mentioned it briefly last time, is you're just thinking backwards. You're not actually thinking about the reagents that you can make, because the actual chemical reaction, this is the confusing part, is going forward. So if you start putting reagents above these arrows, it gets really confusing. So we don't want to do that. And that's why we have this special arrow, which is known as a retrosynthetic arrow, as compared to this very fancy arrow that we have here. Okay, so let's do a couple of examples here. Let's practice. And how about one somewhat similar just to get started? Let's take this alkene. This is what we're going to start with. And let's turn it into this alkene. So this, we do not know of one step that can relocate that alkene from one spot to the next, but we probably know of maybe two reactions that we could use to move that alkene. And we want to ask these questions. So the number of carbons, has that changed? The functional groups, and the location of those groups. Location. In the same order as above? Yep, okay, excellent. So now I'll pause just for a minute or two here and give you a chance, if you want to think about what sort of reaction series could we use to move that alkene from basically inside the ring here to being exo or outside of the ring. And as a hint, these are really, they're all organic 1 reactions. So I'll be quiet for a minute as we tackle this. I'm also hearing some noise. If someone has their microphone on, if you want to mute it, please, unless you want to ask a question. It sounds a little bit like the old modem. I don't know if anyone ever had a computer that you had a modem that you dialed in and would make that crackling noise. Yeah, Abbas, all right. You make me feel young. No. Okay, hopefully everyone's coming up with something. Also reminded me that the phone is I remember when I had my flip phone, that was actually not all that long ago. I guess maybe more like 10 years, but I had to finally get rid of it because the number 7 stopped working on the flip phone. And it was part of my password for my voicemail, which actually caused some trouble. All right, so now we want to change this from one alkene to another. So we're asking ourselves these questions. Does the number of carbons change? And it looks like the answer is no. Does the type of the functional group change? Again, no. We're going from an alkene to an alkene. But the location does change. And so one way of thinking about this is carrying out addition and elimination reactions, actually, to move functional groups around. So we don't know of one way, or one step, I should say, to do this. But what we could do is, we'll go through this forwards, is let's say if we had a bromo substituent here, so it's kind of like the one that we first did. If we had that bromo substituent, then we could actually carry out an elimination reaction. And that would actually give us the alkene where we want it to go. So in terms of our reagents, we could think about adding HBr. And then we'd have to have I'm not going through the mechanism here, but we know that the bromo substituent is going to end at the more substituted carbon. Remember, this is going to pick up a proton, form the more substituted, more stable carbocation, and then the bromine will attack. And then now, if we're going to carry out an elimination reaction, we have to make a choice, because we actually have protons here. I'm only drawing one of the 3, one of the 2 in each of these places that could be abstracted. So we need to choose our base carefully here, because if we choose a small base, then we're going to abstract one of these 2 protons. It'll be the same product in each case, generating the more substituted alkene, but now we're just back to where we started. However, if we choose a big, bulky base, then that will predominantly take off the less substituted proton, generating the less substituted alkene, which is exactly what we want. So let's use its tert-butoxide. Oops, I'll draw the structure here instead. So let's use tert-butoxide, and this is typically used with the corresponding alcohol as the solvent, and we'll heat it up to promote the elimination reaction. So that gives us what we want in 2 steps. Yes, actually, so James, you're right. So what we wanted to do here exactly is we want the Hofmann product. Yeah. And so the first step here, we're generating the Markovnikov product. And then the second step here, we have a choice between, it's known as the Zaitsev or Zaitsev product, which would be the more substituted alkene, or with the bulky base generating the Hofmann product, the less substituted alkene. All right, excellent. Any other questions or comments about that one? Is there another way to do this? There might be other ways to do it, but not a way that is as direct in this particular case. So Ken asked the question about, are there other ways to do this? And what you'll see in these synthesis problems is a lot of times there's many answers, there's many ways to do it. This one here is really, you could use other reagents that might improve the yield a bit, but this would be the most direct way. This brings up a good point here. Actually, let's, do I have it readily available? I'm not sure if I have it here, but I'll mention it anyways. So a lot of times in these syntheses, right, there are multiple ways to do it. Oftentimes what you want to do is to minimize the number of reaction steps. So in this case, if we can do this in 2 reaction steps, that's oftentimes better than doing this in 3 reaction steps. It's for a couple of reasons. One is it's easier. 2 is that each time you carry out a reaction, you're probably going to lose material. So let's just imagine, for example, that this compound is really expensive. It's not, but just pretend that it is. And so if you're going to carry out this reaction, and let's say we actually only had a 50% yield in going from one step to the next, we've already lost 50% of our material. And then if in the next step, if we also had a 50% material, 50% yield, we're actually down to 25% of what we already started with. So we want to minimize the number of steps. What you will find is that if we have synthesis problems in any of our exams, for example, there might be more than one way to do the problem, and that's certainly fine, as long as whatever you do is if it's correct, that's great, and that's the right answer. What I oftentimes do is I'll limit the number of steps in a particular reaction. So I might say that you need to complete, like something like this, I might say you need to complete it in 3 steps or less, which means that this 2-step reaction would be fine for that. And if there's another way that it could be done in 3 steps, that's fine as well. What I wanted to show you here, let me see if I can just